Okay, now, approaching a little more rigor here, we're going to do something similar to what we did here for any old function f of g of x, where f of x and g of x are assumed to be differentiable at all the points we're talking about, certainly at x. Here's a definition of the derivative. Just evaluate the function value, find the function value if you change x by delta x, and thereby value of x plus delta x being close to x. Find the difference that makes in the value of f of x. So that would be the change in the value of f of x due to this change in x. And divide that by the change in x, so you get the rate of change of f of g of x with respect to x, or at least the approximate rate. And of course, there's a limit involved in the rigorous expression. But I'm just saying that the derivative is approximately equal to this if delta x is small. That just means the same thing as the limit, or at least that is implied by the fact that the limit exists. The key idea is, what does g of x plus delta x, how does g of x plus delta x change? Well, you could write out this definition for g of x plus delta x and show that this is so, but local linearity, which I quoted here, I'm using a little more rigorously here. At least I'm stating what it means. Local linearity implies that the change in g is approximately equal to the derivative times the change in x. So that g of x plus delta x is the value of g of x plus the derivative times delta x. Now, why should this be? Well, the derivative is the rate of change of g with respect to x. If you multiply the rate at which g changes with respect to x by the change in x, you get the change in g. That's all this means, and of course this is something you should learn, and should be well ingrained, but almost never is, from a first-year calculus course. And that's from my courses or anybody else's courses. We don't know how to get people to ingrain that. Okay. F of g of x prime, then, is, of course, another way of writing this derivative. I'm writing it this way. Is now approximately equal to f of g of x plus g prime of x, which is the parentheses there, and this minus f of g of x. Now, I was careless up here. I wrote f of x, and I should have written f of g of x. And it should be obvious why that should be f of g of x. And we divide this by delta x, of course. Okay. Well, now what? Well, if delta x is small, then g prime of x times delta x is small. If x is small enough, we can make this as small as we like. So, I'll state g prime of x delta x is small if delta x is small enough. So f of g of x plus g prime of x delta x is just differs from f of g of x by the rate of change of f times this little change in the value of the argument. So by local linearity again, this expression is approximately equal to f of g of x plus the rate of change of f of g of x.
Try to get all of our stuff done by 6.
So we're going to say times f prime of g of x times g prime of x delta x. Then you're going to subtract off the f of g of x. And of course now this expression, f of g of x minus f of g of x is 0, leaving you just this one term. This is just all multiplied. We got a delta x as a factor up here, divided by this delta x, and we get f prime of g of x times g prime of x. Now again, we see that a small change in delta x drives a change in g, which in turn drives a change in f. And the rate of change of the f of g of x function the rate of change of this is just a product of those two rates of change. Okay. Hopefully, this makes the whole idea of the chain a little bit more intuitive. There are other things we can do, magnification models and so forth, and we might do those. But in multivariable calculus now, everything that I did is based on the idea of these rates of change propagating. Now, if you have a function of two variables, and each of those variables is a function of another variable or two other variables or 20 other variables, the change in the ultimate variable, each of the ultimate variables drives a change in your overall function. And we saw what the rules are. Okay. In a very similar manner, it can be written out like this, but it gets a lot longer and a lot more tedious. So we're not going to develop that. But of course, you can always look up the proof. Okay. Very good.